Hello and welcome back. We have understood how SVM works and we even played with a data set, iris data set, and saw how to write code and build a model with SVM algorithm. Let us try to understand how to work with a linear SVC algorithm on a nonlinear data set. On a nonlinear data set, doing a linear decision boundary may be difficult, but when you add nonlinear features, right, polynomial features to the data set, it will become eligible to apply linear SVC also. If you look at this data below, there is a data point belonging to -5, -4, -2, -1 kind of a thing, and these red dots are belonging to one class and the blue dots are belonging to another class, maybe black dots. If you want to do a decision boundary, right, maybe you need to do it here or here. If you do it here, these two data points fall into right side and these four are to right side and these four are to wrong side. The black dots, these four black dots may fall onto the wrong side, and when you try to predict, right, these four black dots may be predicted as red dot, right? So to work with a linear decision boundary, if we raise the data set to the second degree, or there is one feature x, if you add x square to the data set and try to do a graph, right, it actually became a parabolic kind of a structure. Now we can do a decision boundary like that with the support vectors. This has a support vector on the right side and this has a support vector on the right side, black side, and you can do a SVC algorithm, linear SVC algorithm. So when you add polynomial features to the data set becomes eligible to linearly separate the two different classes, or maybe multiple classes, multiple decision boundaries to do multiple separation, right, the data set separation. So that is how the adding polynomial features will help the linear SVC to do a decision boundary on a non-linear data set. So I have taken one example here to do that coding thing, right. I have taken make-moons, a dataset, toy dataset from scikit-learn's datasets. When you visualize this, right, it actually looks like this. The blue squares are one class and the green triangles are other class. They are like this. They are like they're like moons, right? Two moons actually kind of overlapping each other. So we need to do a decision boundary. If we have to do that, right, we have to do like that. So to do that, we need to raise the data set to maybe add more features, polynomial features. I don't know whether you remember or not, but we used polynomial features, a class which can actually do that, adding more features to the data set. But how many polynomials are to which degree we need to raise, we don't know. So it is better we use a pipeline and a gridset CV kind of a tool. Gridset CV can actually take multiple hyperparameters and play with those hyperparameters and give us the best hyperparameter, right? So to do that, I have created a pipeline with polynomial features and then standard scaling and then SVM, linear SVC, right? So what this pipeline will do, when you pass a data set, whether train set or test set, it is going to add polynomial features of the degree you specified. Maybe if you specified second degree, it will add second degree polynomials, 3 third degree polynomials. After adding polynomial features, right, the second degree, third degree polynomial features, the standard scaling will be done, and once after doing standard scaling, the linear SVC will be applied. So in the pipeline there are 3 steps, okay, and we need to pass the hyperparameters, right? In the polynomial features class, the degree is the hyperparameter, and in SVM class, the C is the hyperparameter, which actually controls the overfitting and underfitting, right? To pass those parameters, we can do like this. The param grid, this is the pipeline and this is the param grid, and in the param grid, the variable name in the pipeline underscore the hyperparameter name, and I am passing np.arrange of 1 to 20. That means it's going to generate a numpy array from 1 to 19, and the np.1 to 10, it is going to generate 1 to 9. right? So, and it is going to pass the C value 1 and try to build model, C value 2, try to build a model like that. When you actually do grid set CV here, right, the grid set CV will actually take the 19 values from here and 9 values from here, and it is going to do 19 into 9 number of models, grid set CV. But randomized set CV is not like that. Out of those 19 into 9, right, maybe around 180 odd number of combinations, it is going to choose 10 combinations randomly and try to build models. Okay, so let us see that. Here I took randomized set CV and I passed the pipeline and the param grid. In the param grid I have got 9 into 19 number of combinations, hyperparameter combinations. What are the hyperparameters? Degree of the polynomial and C hyperparameter. And we need to build 19 into 9 number of models. Around 171 models we have to build. And each time we have to do a cross validation. Here I took cross validation as 10. That means 171 into 10. It's going to be 1710 number of models we have to build and find the best model which has got the best hyperparameters. If you use a grid set CV, that's what it happens. But with the randomized set CV, by default it will choose 10 number of the combinations and do models, and out of those 10 it is going to give you the best. So after taking the randomized set CV, I did fit. It built 10 models because the default parameter is 10, the default parameter value. If you look at the API of randomized set CV, here the NITs, the number of parameter settings that are sampled, NITs trends of traits of runtime and quality of the solution. So now by default is 10. If you specify 100, right, it's going to choose 100, right? So it built 10 models, and out of which it found that C value is equal to 1 and degree is equal to 16 as the best hyperparameters. Okay, so if you try to build a model, right, a pipeline, I have taken a pipeline with degree is equal to 16 and C is equal to 1 because that's what the randomized set CV said. That's the best model. So I built a model here. I actually created an object and then trained it by saying fit, right? And now I try to look at how the decision boundary came, right? It is actually good. But if you see this area, right, this is actually green. If some data point, the blue data points in future come here, right, it may actually overfit. But that's okay. For this particular data, the model is working good. Now, for the benefit of doubt, right, what I did is I actually took grid set CV also and did same whatever the param grid stuff, right? Then I got degree 3 and C value 2 as the best hyperparameters. So when I built a model with degree 3 and C is equal to 2, see this? The decision bound is so clear. There are no gaps and other stuff. So always the grid set CV is best, but now if you don't have enough time and resources, you can go with randomized set CV and specify NITs and do whatever the hyperparameter tuning and find the best hyperparameters. The problem with polynomial features is that if you have too many columns in the dataset, you have 1000 columns, if you raise it to second degree, it is going to create n plus t factorial by n factorial into d factorial. That many number of features. It is going to be 1000 plus 1, 1002 factorial by 1000 factorial into 2 factorial. That's going to be like around 500 into 500 into maybe 1000 kind of number of features. It will explode. Exponentially the dataset size will explode like anything, and the memory and processing power are not sufficient because especially the SVM algorithm loads everything into memory and tries to do the quadratic programming to find the support vectors and the decision boundary. It is a too complex of a math. In my view, no need to understand. As long as you can play with the hyperparameters and make the model the best, that is good enough. Okay, so that's about an SVM algorithm and non-linear dataset. In coming sessions, we will understand what is kernel trick and what is kernel SVM, which is a very powerful technique, and it is very pretty much useful in building very complex models on very complex dataset. Dataset may be small, but complex. Thank you.